Estimation and confidence intervals. The key idea of this chapter revolves around the ability to estimate an unknown parameter target. So remember, in statistics, what we want to know is what is true. And what is true is in fact the parameter. Right? Parameter is based on a population, and a statistic is based on a sample. So in this chapter, we take a statistic and we try to estimate the parameter. But since we know that's extremely difficult, we take a sample from the population and use it to estimate the parameter. Point estimates. This is the single value or point derived from a sample and used to estimate the population value. So x bar, or the sample mean, is used to estimate the population mean, mu. S, the sample standard deviation, is used to estimate the population standard deviation, sigma. S squared, the sample variance, is used to estimate the population variance. And P, right, you could see this letter P used to estimate the population proportion pi. The confidence interval estimate is a range of values constructed from sample data so that the population parameter is likely to occur within the range at a specified probability. The specified probability is called the level of confidence. This level of confidence typically implies what we're discussing is middle 90%, 95%, or 99% of observations. So for example, if the confidence interval or confidence level is 90%, then in hypothetical indefinite or infinite data collection, in 90% of the samples, the interval estimate will contain the true population parameter. So a confidence interval includes the point estimate plus or minus a margin of error. For our purposes, we'll be using either a point estimate of x bar or P, which is the point estimate for the population proportion. We will not be creating a confidence interval for the sample standard deviation or sample variance. So what factors affect the confidence interval estimates? And by that, we want to understand what is the width of the confidence interval. So first is the sample size, right, or n. The second is the variability in our population. Third is the desired level of confidence. Let's think about number 2 for a second. So the variability in the population. Let's imagine that every single person in this class was exactly the same height. In that case, our sample size would effectively only need to be 1 in order to capture the true population parameter. However, if we had varying heights, which we obviously do, we would need a bigger sample size. So the more variability in the population, the larger the sample size is needed in order to get a better estimation of the population parameters.
Okay, this lecture is on finding the z-value for our confidence interval, and it involves 3 steps. So step 1. Step 1, we start off with our confidence level, and we divide it by 2. So we want to take the confidence level in the form of a decimal. Specifically, if we're looking at 90%, we want to use it in the format of 0.9. So do we divide that by 2 and we get 0.45. Okay, so the 0.45 is telling us that this encompasses 45% of the one side of the distribution. So step 2. Now what we're going to do is we're going to go to our z-table and we're going to look for or look up 0.45 in the body of the z-table. Okay, now the reason we're looking up in the body of the z-table rather than in the edges, because this is a percentage, not a z-value. Okay, here's our z-table. Now we're going to start scrolling through the z-table until we come up with our 0.45. So you'll notice 0.45 is going to be somewhere in between 0.4495 0.95 and 0.4505, and in fact it's exactly in the middle of it, and I believe this is something we've seen before, and so we use a z-value of 1.65. Okay, so the z-value for a 90% confidence level is 1.65. All right, and that is in fact our step 3, is stating that in step 3, after looking into the body of the z-table, we find that the z-value for the 90% confidence level is 1.65. And so if we were to just jot this down into our distribution, right, effectively we're looking at these areas here, here, right, negative 1.65 to positive 1.65. And since we're looking at the 90% confidence level, we know that this constitutes the middle 90%, and that's what our confidence interval is actually drawing.
Finding the z-value for a confidence level. So there's it's 3 key values that you need to memorize that will make things very, very quick for you. And that is for the 90% confidence interval, the z-score is 1.65, 95 is 1.96, 99 is 2.58, and 80% is 1.28. That confidence coefficient that we just estimated is the probability that an interval estimator encloses the population parameter. That is the relative frequency with which the interval estimator encloses the population parameter when the estimator is repeatedly a very large number of times. Right. The confidence level is the confidence coefficient expressed as a percentage. So if you have a look at this picture here, you notice this line, and you notice that it has a little mu. This is in fact the true population mean of this population. Here you have 10 different confidence interval based on 10 different samples, right? And in each of these cases, you'll notice the length of this blue line is effectively the confidence interval. The ends of it are the upper and lower limit of the confidence interval. The exact middle of each blue line is in fact the mean of that blue line, which means it's the sample mean or the X bar. If you have a look at all of these different samples, we have 10. You'll notice that 9 of those 10 include the true population mean, which is this specific black line, and 1 does not, which means 90%. So some interpretation. For a 95% confidence interval, about 95% of similarly constructed intervals will contain the parameter being estimated, which means if we took another 95% of different types of samples from that specific population of a given size, we would estimate that 95% of them would have the population parameter within that interval. Finally, our equation. So our equation of the confidence interval would be x bar plus or minus z times sigma over the square root of n. So the sigma over square root of n component, this is what we call the standard error. When you multiply the standard error by the z-value, which encapsulates the confidence interval or confidence level, you effectively will capture the true margin of error for this data set. All right, let's look at an example. So confidence interval for the mean, right? It says here sigma known, which means we know the true population standard deviation in this case. The question asks, the American Management Association wishes to have information on the mean income of middle managers in the retail industry. A random sample of 256 managers reveals a sample mean of 45,420. The standard deviation of this population is 2,050. The association would like answers to the following questions. Question 1, what is the population mean? Well, effectively at this point, we don't know what the population mean is. That is the correct answer. However, we can use the sample mean of 45,420 as our estimator. The next question is, what is a reasonable range of values for the population mean? Now, the way we answer this question is by using our confidence interval. Now notice here we have X bar, which will effectively, we will plug in our 45,420 plus or minus Z. Z is going to be associated with the 95% level of confidence, which will of course be 1.96 as we learned in previous slides, times sigma, which is our 2050, right, the population standard deviation, divided by the square root of n, which is 256. And then we will interpret what this means. The next slide is actually a solved example on whiteboard where I will talk you through specifically the steps needed to answer this question.
Example problem. Confidence interval for a mean where sigma, the population standard deviation, is known. Okay, this implies that we're going to be using our Z table in order to build this confidence interval. So let's write out some of the parameters in the problem. The question tells us that n, the sample size is 256, tells us that the sample mean X bar is 45,420. It tells us that the standard deviation of this population is 2,050. For number one, it says, what does the population mean? Bottom line is we don't know what the population mean is, right? However, our best estimation or approximation for the population mean is in fact the sample mean. So therefore, we'll use that approximation to be 45,420. It's our best estimate. So for the part two, it says, what is a reasonable range of values for the population? So what I'm going to use for this problem is I'm going to be using the 95% confidence level or confidence interval in order to build this confidence interval. So the confidence level we're going to use is the 95% confidence interval level. So if you recall from your lecture on finding the z-values for confidence levels, remember the procedure, right? We divide the confidence level by 2, look that up in the body of the z-table, and in this case we'll find that z is equal to 0.96. Okay, so let's build our confidence interval. So our confidence interval is going to be X bar plus or minus Z times sigma over the square root of n. Okay, so X bar we have is 45,420 plus or minus. We have our Z of 1.96 times sigma, which is 2050, over the square root of 256. Okay, so now we need to find what our margin of error is. So what do we know? We know that the margin of error is in fact the entire component here to the right of the plus or minus. So this red highlight is your margin of error. And so that's what we need to find for this problem. So the margin of error is 45,420 plus or minus a margin of error of 251, I believe 0.125. That's the rest of that component there. So technically, we can build a range of possible values here, and we could say that with a 95% level of confidence, the true population mean is likely to be within the following interval of 45,169 through 45,671. Clearly, I did some approximation without using the whole decimal here. You will be required to make sure you use the decimal when you're doing your homework.
What do we find as a result in this example? Well, we find that the income of this group is $45,420 plus or minus $251. In addition, there's 0.125, so about 13 cents as well in addition to this, but that wouldn't make a huge impact on this study. So let's say we were interested in finding an answer to a question like this, to say, would it be reasonable to assume that the true population mean income was greater than 45,000? Why, in fact, the answer would be yes. So how do we interpret this? If we select many samples, or an infinite number of samples of 256, and for each we compute the mean and construct a 95% confidence interval, we could expect about 95% of those intervals would contain the true population mean. Conversely, 5% would not include the true population mean. Next question. The operations manager of a large production plant would like to estimate the mean amount of time a worker takes to assemble a new electronic component. Assume that a standard deviation of this assembly time is 3.6 minutes. After observing 120 workers, which is N, assembling similar devices, the manager noticed that their average time was 16.2. This will be the X bar. We're asked to construct a 92% confidence interval for the mean assembly time. The next slide will walk you through an example of how specifically to answer this question.
Practice question, slide 17. Here we go. The operations manager of a large production company would estimate the mean of the time a worker takes to assemble a new electronic component. Assume that the standard deviation of this assembly time is 3.6 minutes. So what do we have here? We have that the standard deviation is 3.6. So this means that sigma, the population standard deviation, is given and known, and therefore we can use a z distribution in order to do this example. So then the rest of the question is, after observing 120 workers, so n is 120, assembling similar devices, they noticed that the average was 16.2, and this is an average based on those 120 workers. We don't know what the true population mean is. So now we want to construct a 92% confidence level, or a confidence interval. So remember, we have to follow our process here, right? We have to start off by first taking our confidence level and dividing it by 2, and we get 0.46. 2, we're going to look up 0.46 in the body of the z-table. Okay, so we're going to look inside the z-table. So let's bring the z-table over and see what we get. So scrolling through this table, we find 0.46 would be closest to this value here, and we'll say it's 1.75 is that z value. So the z value for a 92% confidence level is 1.75. Okay, so now that we have that, we have our x bar, 16.2, plus or minus 1.75 times sigma, which is 3.6, divided by the square root of 120. So once again, let's find our margin of error. And that margin of error is going to be 0.575. So let's find the range. And the range in this case is 15.625 to 16.775. So basically there is a 92% probability that the true population mean, based on a sample of 120 observations, or an infinite number of sample sizes of 120, that the true population mean is between 15.625 and 16.775.